to 2. And -2 is here. And at this point, the function is not defined. At this point, the function is not defined. That's why we have improper integral of type 2. And to calculate such kind of integral, you guys need to split it into integrals. So you're gonna integrate from -3 to -2. After gonna be -2 to 2. Okay. So you guys can see here, sometimes, the point where the function is discontinuous could be inside of the integral. So we can hide it inside the integral. So in this case, it's easier because you can check, okay, at 4, it's a defined, no problem, but at 1, we have a problem. So it means we know this function is undefined at 1, so we have improper integral for this one. But for this one, the point of discontinuity is inside the integral. If you don't pay attention on this, you can think this is a definite integral, and you can calculate it as a definite integral, and you will get the wrong answer. So be careful. Okay. So let's see how to solve this one. Oops. All right, so I'm just going to show you how to calculate this one. All right, so as I told you here, as I mentioned before, we're going to split it into integral, and I told you the reason. Because -2, at -2, the function is undefined, and -2 is between -3 and 2. That's why I have to split it into integrals. And doing so, you guys will get 2 improper integrals. You can see here, this function now is undefined at -2. Same for the second integral, because both of them now are improper integral. I'm just gonna calculate the first one now, this one, and later we'll see what's gonna happen for the second one. And for the first one, we have improper integral, and as I told you last week, you remove the point where the function is discontinuous, and you replace it by a t, and you let your t approaching to 2 from the left. Why from the left? Because for this integral, my interval is going from -3 to -2, and t has been chosen inside the interval here, and we let t approaching to 2. And when t is approaching to -2, it's coming from the left. That's why we have to calculate the left-hand limit. And doing so, we just want to calculate, this integral, we know it's quite easy. So, the antiderivative gonna be ln of absolute value of x plus 2. So you calculate it at t and at -3. Okay. So now at t, you substitute your x by t is going to be t plus 2. So at -3, when you replace your x by -3, it becomes ln of -1. Okay. So when you calculate here, ln of absolute value -3 plus 2, it becomes ln of absolute value of -1, which is equal to ln of 1, and we get 0. And this is the 0 that we have here. Okay, and now when you let t approaching to 2 from the left, this absolute value is approaching to 0 plus 0 from the right because of the absolute value. Okay, make it positive. So when we are approaching to 0 from the right, the log function is approaching to -infinity. So it means this first integral that we calculate here, we only calculate the first integral, and we got -infinity. So since we got -infinity, so it means we don't need to calculate the second one because the whole thing gonna be just divergent. Even if the second one is plus infinity or minus infinity, this the whole thing gonna be divergent in this case. That's why we conclude. So in this case, my initial integral, which is integrating from -3 to 2, is also divergent because this one is already divergent as we prove it here. And that's exactly what we conclude here. Any question? Is there any question? Any question? All right, you guys are done here. Are you done?
Yes, sir.
All right, thank you. All right, so next I'm gonna introduce a new result called the comparison test. And this test gonna help us to conclude about the convergence or the divergence of very complicated integral. Sometimes our integral could be complicated and we will not be able to calculate it in order to conclude if the integral is convergent or divergent. That's why we will need this test in order to conclude. And what the test says is, anytime you guys have two functions satisfying this double inequality for all x greater than a. So this inequality says, from this inequality, you can say 0 is less than g of x. That's exactly what we here said. G of x greater than 0, so it means g of x so have 0 less than g of x, which is less than f of x. Okay, so this situation gonna give us this 0 gonna be less than integral from a to positive infinity. We know this inequality here, this double inequality is satisfied for all x. For all x starting from a to positive infinity when a is a positive number. Okay, and so a is a number, and the integral of g of x gonna be less than the integral of f of x because of this inequality. So we've seen the integral keeps the inequalities. So when g of x is less than f of x, the integral of g gonna be less than the integral of f. Because g of x is less or equal to f of x. Now, what the condition here says, if the integral of f is convergent, it means if integral of f from 0 to positive infinity is convergent. So we've seen last week, convergence means the integral is equal to a number. That number could be positive, negative, or could be 0. But in this case, it's going to be positive because my function is already positive. Its integral should be positive. So if this is equal to L, a number, L belonging to R, so this means, based on what I have here, so this means integral of G is between 0 and L. Because we already show here the integral of G is less than integral of F. Now, if the integral of F here is already equal to a number L, so it means the integral of G is between 0 and L. But if integral, you guys have an integral which is between 0 and L, it means this is a number. It cannot be infinity. Okay? Because it's between two numbers. So it means this integral is equal to a number, and in this case, it means the integral is convergent, because convergent means the integral equal to a real number. That's the mean of what of the first result here. So it means integral of G is equal to a number n for sure, because if you guys have two numbers, anything between them should be a real number too. And if this integral equal to a real number, it means it's convergent. That's the meaning of this result. Any question? And we'll see later how to apply this. Okay? If you guys have very complicated integral that you cannot calculate, as soon as you find a function which is greater than that one, for which the integral is convergent, it means your integral is also convergent. This is, how to use it. I repeat again. Let's suppose that you guys have integral of f, which is complicated. Okay, integral of g, sorry, which is complicated. what you have to do in order to prove the integral of g is convergent, even if you don't know its value, you have to find a function f which is greater than g, and g should be positive. If you find a function which is greater than g and that function is convergent, automatically your integral g gonna be also convergent. That's the meaning. And that's exactly what I prove here. If my integral of f is equal to a number, knowing this inequality, it means the integral of g is between 0 and a positive number. It means the integral of g is also equal to a positive number. And this is what we mean by convergent. Second case here is this. Now, if integral of g now is equal to is divergent, but divergent means the integral is either equal to positive infinity or negative infinity. But since my function g is already greater than 0, its integral cannot be negative infinity because it's positive. The only way is just to get a positive infinity, divergent. Now, if integral from a to positive infinity of g of x is equal to positive infinity, okay? If this integral is positive infinity, it means it's divergent. In this case, it means based on this, when you combine these two situations, it means 0 is less than infinity, which is less or equal to integral of f, right? Because we prove integral of f is greater than integral of g. But as soon as integral of g is equal to infinity, what can we conclude from here? Is it possible to get this integral equal to a real number? Yes or no?
No.
No, because we cannot find a number which is greater than infinity. This cannot be a real number. The only way to get this inequality valid is this should be infinity. So it means this involves the integral from a to positive infinity of g is also equal to infinity. And this is, it means the integral, or f, sorry, I said g. Because this integral is greater than infinity, so it means it's just equal to infinity because we don't have something greater than infinity. So it means the integral is divergent. Basically, it means anytime you guys want to prove an integral is convergent, you have to find a greater function for which the integral is convergent. If you want to prove the integral is divergent, you have to find a similar function for which the integral is divergent. And you conclude. Any question? All good? Any question before I erase, what I wrote?
No, sir.
All right, thank you. All right. before just doing an example, I'm just going to give you the second FTC. Last week, we've seen the first FTC, and here is the second one. Okay. And what the second FTC says is, if you guys have this integral from A to B, this is an improper integral of type 2. Even if you don't have infinity, it's improper integral because you guys can see this function 1 over x minus a is undefined at a, because when you substitute x by a, you will get 1 over 0. That's why this is improper integral. It's just the example that we did today. It's similar at the beginning of the class. The second integral is also, we have p here. This is also an improper integral of type 2 because when x equal to b, going to be undefined here. So this one is improper integral because of a, the second one because of b. And what the second p-test says, anytime you guys have this kind of integral, they are convergent if p is a number, is any number less than 1. And they diverge if p is greater or equal to 1. You guys can see it's a little bit similar to the first p-test that we've seen last week, but be careful, they are different. For the first p-test, the convergence is obtained for the values of p greater than 1, the opposite what we have here. In this case, we have the convergence when p is less than 1. And I'm just going to give you some example to see exactly what I'm saying. Zoom out. So let's say you guys have this first example here. And for this one, we have this situation, integral from a to b, and at a, my function is undefined. That's exactly what I have here, integral from 2 to 7, and at 2, my function is undefined. And based on what the term says here, this integral is divergent because p equal to 3 by 2, and it satisfies this condition. And we've seen any p satisfying this condition here, the integral going to be divergent. And for the second situation here, we have integral from -3 to 5. It's similar to this one, from -3 to 5, and at 5, my function is undefined. Again, here, my p is equal to 4 over 5, which is less than 1. And when the p is less than 1, the integral is convergent. Last case. So this one is similar to this one too, even if you don't have minus sign, because of here we have -3. Okay, so here my a equal to -3. That's why it becomes x minus -3. It becomes +3. Again, you can conclude this integral is convergent because p equal to half, which is less than 1. That's exactly what we have here, what the second p-test is. Any question?
Sir, it is the reverse of the p-test one.
Pardon?
It is the reverse of the p-test one because if p is greater than 1, it is convergent in test 1.
Yeah. Here is the opposite.
Yes, it is the opposite.
Yeah. Now don't mix up the two tests, because the first test that we've seen last week was for the first type of improper integral. The first type of improper integral is when you guys have infinity. So here you see you have two real numbers, a and b. That's why it's different. Okay. Now, before doing an example related to the comparison test, I'm just gonna give you a couple of improper integral, and you guys can tell me whether or not they are convergent or divergent by using first or p-test, depending on the situation. Okay. The reason why we need the p-test is gonna be our reference integral when we apply the comparison test. Because based on what the comparison test is, we have very complicated integral and we compare it with another integral. That's why we call it comparison test. We have complicated integral and we're gonna compare it with another integral that we already know if it is convergent or divergent. Okay, it's gonna help us now to conclude. And if you guys use the comparison test, you have always to compare your integral with one integral coming from the comparison test. That's why you need them, because you already know in which condition, under which condition, your improper integral is convergent or divergent depending on the p-test. That's why, since you already know all this information about the p integral or the p integral similar to the p-test, you have always to compare your complicated integral and one of the integral coming from the p-test. And then you can conclude from there. Okay, so that's why the first step is to know exactly how works the p-test. All right, I'm going to give you some examples. Okay, I'm gonna give you 30 seconds and you guys can tell me if which of this integral is convergent and which one is divergent. Okay, you guys are done? What do you think about the first integral? So here it's the x squared.
Divergent.
Divergent.
It's a divergent because equal to 2 by 3 based on the first test, first P test. The first P test says when P is less than 1, the integral is divergent. And it's less than 1. Is it okay for all of you guys? So it means if you calculate this integral, you will get positive infinity. And you can verify it at the end of the class if you guys want. Antiderivative is not complicated. Now, what about the second one?
Divergent.
It's a divergent. You use the second P test. As you can see, P is greater than 1, 5 by 3. So here is also divergent. Divergent because of what the second P test says. The second P test that you have here in front of you. Because here my P satisfies this condition, greater than 1. You see, for the first P test, the divergence is obtained when with less than 1, while for the second one, the divergence is obtained when we greater than or equal to 1. So here, it's a 5 by 3. And it's greater than 1. And what about this one, the third case?
Convergent.
Pardon?
Convergent.
Convergent because P equal to, what is the value of P?
2/3.
2/3. It satisfies this condition, less than 1. Second P test, because we have second type of improper integral. It is similar to this one when you substitute P by 2/3. So in this case, it's going to be convergent. By the second P test. In this case, P equal to 2/3. And it's less than 1. And for the last one here,
Convergent.
Convergent by the first P test. Because of infinity, you have to use the first P test because we have the first type of improper integral. So the last case here is convergent by the first P test. So in this case, P equal to 6/5, which is greater than 1. Any question? You guys have questions? This is the right time. And we will get our last quiz next week. And it will cover the improper integral that we did last week and today, and also the partial fractions decomposition. Okay, so we'll do more practice tomorrow and later today, maybe when we have time. Is there any question? Can I erase this?
Yes, sir.
All right. So now we're ready to apply, the comparison test, because as I told you, the comparison test say you have to compare your complicated integral with another integral that you already have a lot of information about its convergence. And that integral going to be always an integral coming from the first or the second P test, depending on what kind of integral you have in your question. All right. So here is our first example. We want to integrate from 0 to positive infinity e to the power negative x u squared dx. And this integral is in fact complicated because we don't know the antiderivative of e to the power negative x squared. So be careful, don't say it's equal to the same function. If the square wasn't here, yes, it's gonna be easy. If the square wasn't here, if it was just x to the power negative x, yes, the integral gonna be too easy because the antiderivative gonna be exactly equal to minus e to the power minus x. And we can calculate the limit. Because of the square, we don't know the antiderivative. Okay, now I have to use a comparison test. But if I want to use a comparison test, it depends on the type of integral that I have. Is it a type 1 or type 2? So what do you guys think? Is it type 1, improper integral of type 1, or improper integral of type 2? Pardon? 1, exactly. Why? Because of infinity. Last week, we've seen as soon as one of the limit of your integral is equal to plus or minus infinity, you have an integral of type 1. Type 2 is when you have two real numbers and at one point in the interval of integration, the function is discontinuous. Okay, so here, since you have infinity, it means you have improper integral of type 1. So it means you have to compare this improper integral of type 1 with an integral coming from the first p-test, because the first p-test is used for type 1. Second p-test that we've seen today is used for type 2 improper integral. So it means now forget about type 2. We have to use type 1. And what type 1 says, if you have a, which is a positive number, integral from a to positive infinity 1 over x to the power p dx converges if p is greater than 1. That's what the first pt says. So it means we have to compare our integral with an integral similar to this with the right p in order to be able to conclude. And to use similar integral, the bottom here, the lower limit should be greater than 0, not equal to 0 as we have here. That's why I'm gonna split my integral here into integrals. I'm gonna integrate from 0 to any number. I repeat again, why I'm doing this is I wanna get the bottom here equal to a number which is greater than 0. Since I have 0 here, I cannot use the improper integral here, the first p-test, because the first p-test here, the integral start at a positive number, and here we start at 0. That's why I'm gonna just take 1. You can take whatever you want. It could be 1 or something else. And you have to do this anytime you guys realize you have 0. But you don't have 0, you don't have 2. Okay, if it was just positive number, we don't need to split it. So you can use from 0 to 1 or from 0 to 100 or from 0 to whatever you want as soon as it is positive. It's gonna be integral of minus x u squared plus integral from 1 to positive infinity. And now you guys see my a is greater than 0. That's the only reason that I split it, because I want to get the bottom equal to a number greater than 0. And e to the power negative x, right? And this is improper integral of type 1 because of the presence of infinity. So what about this one? What kind of integral is it? You guys can tell me? The first integral, is it improper integral of type 1, type 2, or definite integral? So type 2. So type 2 means we have a number between 0 and 1 where the function is undefined. What is that number? You say type 2. Type means there is a number between 0 and 1, 0, 1 included, where the function is undefined. Is there any number like that? What is the domain of this function? You guys can tell me, please. E to the power minus x squared. What is the domain? What is the domain of an exponential function? You did it in 1500. The domain is equal to all real numbers. As you can see, this is always defined, no matter what is x. So it means this is not an improper integral. It's in fact a definite integral, always defined. This function is continuous everywhere. In particular, it's going to be continuous between 0 and 1. We don't have any point of discontinuity or infinite discontinuity. Okay? So it means this is not a problem because it's a definite integral that we've seen, in the previous chapter. So definite integral is always a number. Okay? It means the convergence will depend on this part. It means, my initial integral from 0 to positive infinity is convergent if and only if this second integral is convergent. That's why we only need to prove the second integral is convergent, because this is already equal to a number. Even if we don't know its value, but it's a number because it's a definite integral, my function is always continuous between 0 and 1. And we've seen any continuous function is automatically integrable. Okay, the first part when we was defining integral, definite integral. Is it okay? Okay, so that's exactly what I mentioned here. I split it into integrals in order to get the bottom here equal to a number which is greater than 0. And as I mentioned before, you can introduce any positive number. Doesn't matter. At the end of the day, you will get the same exact conclusion, same solution. This is a definite integral because my function e to the power negative x squared is always continuous everywhere. In particular, going to be continuous in this interval 0, 1. That's why it's going to be definite integral and it's going to be a number. And as I said, now we have just to prove this improper integral is convergent in order to be able to conclude the initial one is convergent, because if this is convergent, it's going to be a number plus this is already a number, and it means the whole thing going to be a number. And to prove it, as I said, we have to use a function similar to the function coming from the first p-test, and I told you the reason before. And that's exactly what I'm going to do. I'm just going to incorporate here an exponential function and a power function. And we know the exponential function as faster and are greater than the power functions. So since I have x squared here, that's I said, you know, e to the power x squared is less than e to the power x squared, because we know this. For all y, we know y is always less than e to the power y. That's what I use. And I substitute, this is true for all y. In particular, is going to be true when y equal to x u squared. It's coming from there. And the second part here, because you squared, that's why it's going to be just greater than 0. Okay. Now I'm going to take the inverse 1 over x squared, going to be less than 1 over, 1 over e to the power x squared, going to be less than 1 over x squared because of this inequality. You guys can see, anytime you guys have an inequality, when you switch by taking the inverse, the inequality gonna change direction. So for example, here, let's say you guys have 2, which is less than 3. In this case, 1 over 3 gonna be less than 1 over 2, right? 1 over 3 is less than 1 over 2 because of this inequality. And see, 1 over 3 is 0.3 and 1 over 2 is 0.5. And that's exactly what I use here. This is my 2 less than 3. So that 1 over 3 gonna be less than 1 over 2. And 1 over, if you take this denominator here, you send it to the top. This denominator, you send it to the top, you will get exactly this function. And that's what we did. I took this and send it to the top. It becomes e to the power negative x squared. Now I have my p function similar to the function coming from the p-test. That's what I told you. You have to compare your complicated integral with an integral similar to one coming from the test. And based on the p-test, this integral is convergent because p is equal to 2. That's exactly what I have here. P equal to 2. That's why my integral is convergent. I use p-test. And to conclude, I'm going to use exactly what the comparison test says, because if this inequality is satisfied and the integral of this one is equal to a number, this one doesn't have choice to be equal to a number because its integral going to be between and a positive number. Okay, that's exactly what the comparison test says. So since this is the integral of this one is convergent by the p-test, so it means by comparison test, this integral going to be also convergent, and done. Any question? Now what we prove is this convergent integral from 1 to infinity. To conclude, as I told you, if this integral is convergent and this one is already equal to a number, it means the whole thing here is convergent, and this is our conclusion. Any question? All good?
Yes, sir.
All right. Let's now see the second example. And for the second example, we just want to prove, the integral is divergent. And as I told you, if you want to prove the integral is divergent, you have to find a similar function for which, the integral is divergent. That's exactly what the p-test, the comparison test says. Okay. All right. Let's see. Now, for x greater than 1, because my integral start at 1, that's why you guys can see the integral. It's integral from 1 to positive infinity. That's the only reason I wrote here for x greater than 1, but this is always valid, no matter what is x, because we know the exponential function is always positive, e equal to 2.7 approximately, so e to the power minus x is always positive. That's why positive number gonna be greater than 1. Now I'm gonna divide this by x. I'm gonna divide here by x, I'll get this, and gonna be greater than 0 because x is greater than 1. That's why 1 over x for sure gonna be greater than 0. And you divide here again by x, you will get this part. And by the p-test, this integral is divergent. It means this integral, the integral of this function equal to infinity. That's the meaning. Here p equal to 1. First p-test says when p equal to 1, it's a divergent. So it means, the integral of this function is divergent, equal to positive infinity. It means this one doesn't have choice to be also positive infinity because this is positive infinity. And that's what we conclude here. It's also divergent. Any question? So let me know whenever you're done. All good?
Yes, sir.
All right. So this example, conclude this chapter. And I'm just gonna give you, I don't want to start a new one. I'm just gonna give you some examples coming from past quiz, and then you guys can try. All right, I'm just gonna give you this one. Okay, you guys can try to do this one. So you notice here, since we have infinity, it means we have the improper integral of type 1. And for improper integral of type 1, we have to compare our integral with an integral similar to the integral in first p test, because we have type 1. Type 1 first p test, type 2 second p test. Okay, I'm gonna let you try to do this one. So you guys done? Okay, let's see how to solve this one. So you guys can see your integral start at 3 to positive infinity. So that's why I can say, okay, for x greater than 3 means for x belonging to the interval. So this writing means for all x belonging to the interval x squared, and it's going to be also positive, right? Because you know the smallest value of x is 3, but if you take 3 squared, going to be 9 minus 2 going to be 7. It means the smallest value of this is 7, which is positive, and it's less than 9. Okay, and I'm going to take the square, the root cubic. So this means 0 is less than cubic root of x squared minus 2. I'm just working with the denominator here. So which is less than but we know this is just equal to x to the power is it okay up to here? But this function here, the root cubic, is in fact my denominator. I just want to send it, write it as a denominator. So it means I have to take the inverse. So this means 1 over cubic root of x squared minus 2. So this is going to be greater or less than 1 over this. It's going to be greater than 1 over, because when you take the inverse, as I told you, we did one example before. So since this term here is less than x to the power 2 by 3, it means 1 over x to the power 2 by 3 going to be less than 1 over cubic root of x squared minus 2. And since my x is greater than 3, it means this is already positive because x is positive. And I'm just going to keep this. Because I found a function which is less than my denominator. Now I'm going to work with the numerator. Okay. I know here cosine x in addition here. I know cosine x is between, what do you guys think? Cosine x is, no matter what is x, this is always between -1 and 1, right? For all x, in particular for x greater than 3. And when you square it, the square of cosine going to be between which values? What do you guys think? If cosine is between -1 and 1, the cosine square going to be between 0, 1, exactly. because when you square a number, it becomes a positive. It's going to be greater than 0. But if you square a number which is less than 1, it still be less than 1. So for example, if you take 1 by 3, you square it, it becomes a number less than 1. Any number less than 1 has its square less than 1. And you can see here my cosine square now is between 0 and 1. But what I want is minus square. I have to multiply by minus 1. Minus cosine square going to be, in this case, between which values? So you guys can tell me if my cosine square is between 0 and 1, minus cosine square going to be between? Hello?
Minus 1 to 0.
Exactly. If you guys have a number between 0 and 1, it means its opposite going to be between minus 1 and 0, right? You have 2, let's say you have 1 by 2, which is between 0 and 1. The opposite, negative 1 by 2, going to be between minus 1 and 0. You multiply, going to be just here between minus 1 and 0. Now I'm going to add 2. I'm going to add here plus 2 in order to get 2 minus x squared. If I add 2, I'll get here minus 1 plus 2 going to be plus 2. I'm going to add 2, right? And I'll get here, I'll get just, this is 1. It means 1 is less than 2 minus and I prove now my numerator is less than 1. Right? Now from here, I'm going to divide this because I'm trying to use now this part here. I'm going to divide the whole thing here by 1. I'm going to divide by x to the power 2 by 3, which is a positive number. 1 over, I'm going to divide, the left hand side here by x to the power 2 by 3. Is going to be, and this is also positive, right? Based on this. And you divide again here. So from this this step here, I just divide on both sides of the inequality. I divide by x to the power 2 by 3. Since I divide by a positive number, I'll still get my same inequality. Is it okay up to here? Any question?
Sir, why are we dividing it by x to the power
Yeah,
of, yeah.
because I'm trying to use this part in order to get my function here. This is a numerator, you see? I'm trying to get this, all this. I told you, when you guys have a improper integral of type 1, you want to compare your integral with an integral similar to the one coming from the first p-test. And one from the first p-test is going to be always 1 over x to the power p. That's why I'm trying to get 1 over x to the power p. and I divide here because I already have this part here. Okay, and from this part here, this means this is less than 2 minus cosine square x over cubic root of that. The reason why I divide here, because I of this what I got here, because I multiply up here from this inequality, I multiply the numerator by 2 minus cosine square. If I multiply here the 2 minus, I'll get this part. I multiply the right hand side by 2 minus cosine square, I'll get this part. And now this is the function that I want to integrate, is my function here. And I prove now the function is less than so it means 0 is less than 1 over x to the power 2 by 3. I just copy this part here, the first inequality, and it's less than this one because this part here is less than this function, which is less than this one. So it means 1 over x is less than 2 minus cosine square. And now we're ready to conclude. Right? And by the p-test, the integral of this function is convergent or divergent. By the first p-test, is the integral of this function convergent or divergent?
Divergent?
Divergent, because p is less than 1. So when this integral is divergent, it means this integral is divergent by the comparison test. And we conclude. Okay, so conclude, we can say by the p-test, the first p-test, okay, by the first p-test, the integral from 3 to positive infinity of 1 over x to the power 2 by 3 is divergent, because here p is equal to 2 by 3 and it's less than 1. But if the integral of this function is divergent, means the integral of this function, it means, the integral of this function is equal to infinity. That's the meaning. Oops, oh, this guy coming in, just, I erase it. Okay, so you already have the solution here. So we already wrote all this. I'm just going to show you the conclusion here. So by the p-test, we already proved this part here. So since this is a convergent by the comparison test, so this integral is also convergent. Yeah, I was admitting one guy who was out and it is all thing. P-test, this the integral here is divergent. So it means the integral of this function is going to positive infinity. In this case, this integral going to be for sure equal to infinity. Doesn't have just to be infinity, because cannot be greater than infinity. Any question? Is there any question? You guys let me know whenever you're done. Any question?
No, sir.
All right, so if there is no question, I'm gonna let you go. That's all for today. And before letting you go, give me time to take the attendance. All right, Magabet. Thank you. Fatima.
Here.
Thank you. Alamin.